In this video, we're going to talk about something called the class equation, which is really a theorem. I want to write this down, a theorem about conjugacy classes in a finite group. Just to help set the stage here, I'm going to introduce an example. We're going to use the example of none other than D4, the dihedral group on a regular fourgon or square. And just to help make things a little bit more efficient here, I'm going to throw in the image of the Cayley table for D4, so we don't have to do all of the calculations from scratch. So let's see if I can find that. Here we go. This is the Cayley table for D4. I'm just going to move that up here, out of the way. Let's put it up there. Okay. So the question I want to ask here, just by way of introducing what the class equation is I want to ask, what are the conjugacy classes of D4? So one thing I want to recall here is that there is a conjugation action of G on itself, that is G on its own elements, for any group G, not just finite groups, not just D4, for any group G. Okay, there's a conjugation action. That action is G acts on X by sending X to GX G inverse. In other words, acting on X with G means conjugating X by G. That's the action. So we're going to illustrate how that conjugation action works for D4, and then we're going to notice a couple of things, and then we're going to say why we should have expected those couple of things to happen. Okay, so let's start by figuring out what is the conjugation or conjugacy class of R0. Okay, so we could try, for example, calculating, just as an experiment, D R0 D inverse, where D inverse is just D because D is its own inverse. Any reflection in D4 is its own inverse. Well, D R0 D is, well, R0 is the identity, so that's just D D, which is just R0. In fact, R0 commutes with everything, so I could have just said, well, we could switch these two, and I've got R0 times D times its own inverse. And that's going to be the case no matter what. If X is any element of my group, I've got an R0 there and X inverse, then the R0 is going to commute because it's the identity. And I'm going to be left with R0. So the conjugacy class of R0 contains just one element, it's R0. Okay, so let's try a different one. Now I don't want to get too far out of bounds because I want to keep my Cayley table in the picture here. What about R90? Okay, well, if I take R90 and conjugate with some other rotation, like let's say R270, so then I'm multiplying R270 on the left and its inverse on the right. The inverse is R90. That's the inverse of R270. Well, again, R90 is going to commute with any other rotation, so I can just move R90 out to the left and leave myself with R270 times R90. Those two cancel each other out. They're inverses, and I'm left with R90. So you might think, well, the conjugacy class of R90 is just going to be R90, but it's not quite so. Actually, if I conjugate R90 with something else, let's say H, and then put H inverse on the right, but as always, H inverse is just H. It's a reflection. It's its own inverse. Well, R90 times H in my Cayley table, R90 times H, and now I'm shamelessly looking things up because I really don't want to have to do all these calculations by drawing squares. It looks like R90H is D prime. So that's H D prime, and then using my table to calculate H D prime, H D prime looks to be R270. Okay, so that means that R270 is a conjugate of R90. Those are in the same conjugacy class. R90 is also a conjugate of R90, so R90 is also in its own conjugacy class. But it's going to turn out, and you can verify this by checking other rotations, checking other reflections, doing other conjugates. The conjugacy class of R90 only consists of those two, R90, R270. So that's another conjugacy class. R180, it turns out, actually is its own conjugacy class. I'm going to zoom out a bit so we can keep scribing here. There we go. Don't want to take the table out of view. But for R180, the conjugacy class is just R180. Every conjugate of R180 is just R180, which one thing that means, by the way. So what I'm claiming here, and you can verify this just by checking elements one by one, this is always R180. If I multiply on the right by x on both sides, I get x R180 equals R180x, which means this is another way of saying R180 commutes with everything. R180 belongs to the center of this group. You may not have known that, but actually there is a non-trivial center to this group. It consists of the identity R0 and R180. Okay, let's do a couple of other ones here. Okay, so we have conjugacy classes for R0, for R90, and R180, and I think those accounted for all of the rotations. What about D? The reflection D. Well, if I take D and conjugate with R90, so R90 on the left, R90 inverse on the right, R90 inverse is R270, then just doing the calculations one at a time, R90 times D is going to be H, and then H times R270, again using the table, H times R270 is D prime. Okay, so D prime is a conjugate of D. What about if I conjugate with something else? Let's try a reflection, because I know that conjugating with the identity or with R180 isn't going to do anything, because those are both in the center. But what if I try something like, I don't know, HDH? What would that be? HDH, well, HD, it looks from the table to be R90, and then multiply that by H. R90 times H is D prime. So it looks like I can get two things as conjugates of D, D and D prime. So that conjugacy class will be D and D prime. And I'm going to leave it as an exercise for you to show that the conjugacy class for H is HV. You can get both H and V in the same conjugacy class, but no others. So what conjugacy classes do we have altogether? We have this one, the identity. We have this one, not the identity, but still in the center. So that's a one-element conjugacy class. And then everything else seems to have two elements. We've got R90, R270. We've got D and D prime. And we've got H and V. And one thing that we noticed is a conjugacy class has one element if and only if that element is in the center. That is, commutes with everything. Okay, so what does all of this mean? Well, for one thing we can notice about all of this, I mean, besides just that we have a couple of singletons here, is that we have 5 conjugacy classes, which 5 is not the most expected number, I'd say, but they are all disjoint from one another, and they make up the entire group. They have to make up the entire group because every element has to have a conjugacy class. I mean, you can always take conjugates of an element and construct that element's conjugacy class, but the fact they're all disjoint is kind of interesting. But it's also something that we should expect. Here's why we should expect conjugacy classes to be disjoint. Conjugacy classes are disjoint because they're orbits of a group action. They are orbits of the conjugation action. They're orbits. And there's another thing too. Notice that in this case, we had conjugacy classes with one element. We had conjugacy classes with 2 elements. And that is also something that we may have been able to project, or at least part of it we could have. How big is a conjugacy class? That is an orbit. How big is a conjugacy class? Well, one thing that we know about orbits is that their size is constrained by the orbit stabilizer theorem. So by the Orbstab theorem, the orbit of an element times, or that the order of the orbit times the order of the stabilizer of an element is equal to the order of, in this case, D4, the order of the group that is acting. Well, what is the stabilizer of an element under the conjugacy action, or conjugation action? Well, what does it take to stabilize something? If I conjugate x with g and get x back, then that means that gx has to have equaled xg, because I'm multiplying on the right on both sides by g. That means that g is something that commutes with x. So that means g is in the centralizer of x. So the size of the stabilizer, that size is going to be the size of the centralizer of x. And then the size of the orbit is going to be the size of the conjugacy class. And then the size of D4, that's known. That's 8. But in general, I guess if that's a group G, then this would be the order of that group. This is a key insight. And this is part of what gets encoded in what we call the class equation. The class equation is so nondescript sounding. It's like, well, this is a class, and here's an equation. But it's actually, the class in class equation refers to conjugacy classes. So let's see if we can write this down. So, okay, so just to review or recap, conjugacy classes so here's just some facts. Number one, they make up all of G, whatever the group is. Number two, they're disjoint. If conjugacy classes share anything, they share everything. Number three, the size is the order of G over the order of the centralizer of one of the elements. Okay, and that's because of this Orb-Stab theorem here. If we look at this, the size of the conjugacy class is this divided by this. And finally, these are singletons, or single element sets, if and only if x belongs to the center of the group. Knowing those four things, we can put together what's called the class equation. So here it is. The order of the group, that is the number of elements altogether in the group, is equal to, and I think I'm just going to write this down. I'm going to say it's equal to the size of the center of G plus the sum, and I'm going to say what the sum is over in just a moment. It's the sum of G over the order of the centralizer of x. And what is x? The sum ranges over 1 representative x of each non-singleton conjugacy class. It's a little bit of an awkward way of saying it. I think the book may have a better way of saying it. But what this means is that we take each conjugacy class that does not represent the center of the group, and we take one representative. Because what we're doing here is we're adding up the sizes of all of the conjugacy classes. That's what this represents. This is the sum of the sizes of all conjugacy classes of G. Okay, and why is that equal to the order of G? Well, it's the order of G because the conjugacy classes make up all of G. That is, every element of G appears over here somewhere and appears only once. There's no overlap among the conjugacy classes. And just to review, this term represents the size of a conjugacy class by the orbit stabilizer theorem. That is, this is the entire group, or its size. This is the size of the centralizer. Dividing those according to this equation here gives me the size of one orbit, or one conjugacy class. This does not represent the size of one conjugacy class. It represents the collective size of all of the singletons, because each singleton represents something in the center of G. So when you look at this, don't think of one class. Think of a lot of little classes, each with its own single element, each of which commutes with everything. Whew. Okay, so that's the class equation. And let's just to wrap up, let's say what this looks like in the case of D4. That's a nice little closure there. So in particular, the size of D4 equals the size of the center of D4, which, interestingly, was not 1, it was 2, plus the sum of the order of D4 over the centralizer of X, where the X's range over one representative of each non-central conjugacy class. So in this case, this was 2, consisting of R0 and R180. And then that means this sigma here is going to end up representing 6. Okay, that's not a sum over 6. I'm just saying that this whole sum is equal to 6. But what were these? These were, let's see, they were D, D prime, HV, and R90, R270. And just to analyze why we had 2 in each case, because each of these was 2, well, this was 8. The numerator was always 8. That means that each centralizer has to be 4. And we can actually check that out. If you think about R90, what is its centralizer going to be? What's going to commute with R90? Well, that's going to be R0, the identity, R180, which is also in the center, and really any rotation is going to commute with R90. Any rotation is going to commute with R270. So the centralizer here was just all of the rotations, 4 of them. So we're dividing 8 by 4 and getting 2 different things that are in the conjugacy class. Over here, H and V, again, I can identify 4 things that centralize these elements. R0, which is the identity, R180, which commutes with everything, and H and V. H and V commute with each other. Same here, R0, R180, D and D prime. That would be the centralizer of this set. So anyway, the moral of the story is we can represent the size of a group as this weird sum, which actually has a very deep meaning. It's the sum of the sizes of all of the conjugacy classes. Why would we want to do this? Well, you'll find out in the next video.